Well, there's two separate variables. One is the weight. Another is what's the explosive payload inside it. So the explosive potential is one thing, but bunker busters are not really made for their explosive potential. Like when they hit the ground, it's not like, it's like, yes.
Depleted uranium.
Can't wait.
Depleted uranium. Depleted uranium.
Yeah, depleted uranium is just uranium that has, the 235 has been worked out. We can talk about that later. Usually it's more of the heavy isotope, less of the nuclear active isotope.
I heard they use depleted uranium.
Yeah, that's right. It's a waste product. At that point, it's just really heavy lead.
Cool.
Are we all done talking about that? Next, check this out. When you get the uranium ore out of the ground, there are two isotopes that are stable on the Earth. There are two isotopes that you would find on our planet. Uranium-238 is almost all of the ore, 99.28. You have to write that down. That ore is almost entirely the heavy isotope. And very, very little of the raw uranium is light, 0.72. And I have a concept for you, so I need to explain it outside of the uranium, and then we'll come back to the uranium. So here comes my concept. Here comes my basic concept. Let's imagine I love students with flower names, which I do. So for the sake of conversation, I've got a thing for people with flower names. In other words, all of you are useless except Violet. Anybody else that I forgot has a flower name? No, I usually remember that. So, you're all waste as far as I'm concerned.
I'm a tree though, so.
Cedars have little splinters, and when you take a nap against the bark, those little splinters get into your back, and then you have like weeks of picking splinters out of your back. I hate cedars. When you burn them, yes, be quiet, Ginger. Okay.
By themselves.
That was pretty funny. Okay. So I've got my violet, and I've got all my riffraff. How would I make my teaching experience better? How would I enrich my teaching day? If we assume I can't change your names, then the other alternative is get rid of some of you. So look, right now, 1 in 33 has a flower name. That's a 3% success rate. If I got rid of half of you, all of a sudden it would be 3 out of 17. That's like a different percentage that I can't do in my head right now. That's pretty good, like 30%. Then if I got rid of more of you, it would be like 1 out of 5. That's pretty great. If I got rid of more of you, then it'd be like 1 out of 2, 50-50. And then I could be really psyched if I got rid of the last one that doesn't have a flower name, right? That's the process of enrichment. You take the ore, you grind it up, you spin it really fast, and you shave off the heavy stuff on the bottom. Then you grind it up, you spin it really fast, then you shave off the stuff on the bottom. Then you grind it up, spin it really fast in a high-speed centrifuge so that the heavier grades of uranium are all packed down to the bottom of the plug of uranium. Take it out of the plug, cut off the bottom, you grind it up into a powder, and then you spin it really fast so that every time the lighter stuff is on the top of the plug, and then you get rid of the heaviest. You grind it up, that's called uranium enrichment. And by the way, That is the entire thing. How many of you have heard that Iran is in trouble for enriching uranium? That's what they're doing. I just described all of it. All that's left now is details of how to design a centrifuge that can take that much weight. That's it. That literally is the whole high-tech uranium enrichment, is grinding up and spinning uranium. That's enrichment. Yeah. Ore is raw material like you get it out of the ground. Yeah.
What's the benefit of the lighter stuff opposed to the heavier stuff?
I'll get to that. So watch me. Normal uranium or uranium, the stuff you dig out of the ground. By the way, in Carpinteria / Summerlin, Montecito, like you can go dig it up. Like you can make mines here if it wasn't such expensive real estate. Uranium, you dig it up, is almost entirely 238, but has a small percentage of 235, and 235 is special. I'll explain why later. When you get rid of, please look up, when you throw out some of the 238, when you get it up to 97% 238 and 3% 235, that's called fuel grade. You can run a nuclear reactor with 3 to 4%. If you can get it to about 90% uranium 235, that's weapons grade uranium, highly enriched uranium. We are all nervous that if Iran can go from 0.7 to 4, they can go from 4 to 90 and build bombs. I mean, I don't know. Some people are nervous. I'm not actually that especially nervous. Yes?
What happens, because you said like the bombs, like the bunker busters, aren't exactly like very explosive at all though. So
Right.
what happens when you shave off the heavy stuff that makes it so explosive?
You use just the heavy stuff to make the bombs. So those bunker busters are depleted uranium. It's been depleted of the 235. The 238
So what makes
is
that
just
so
a
much
heavy
more-
ass metal.
What makes it so much more explosive?
Nobody said anything about explosive. Bunker busters are not explosive. They're just heavy.
So like nuclear is really explosive. So.
Actually, we haven't talked about nuclear at all yet, and the nuclear reaction is totally out of this conversation. There's nothing nuclear about anything I've said so far. We can talk about why nuclear is explosive. We will. And by the way, it's actually expansive, not explosive. Distinction between modern gunpowder and black powder, but it's expansive, and we'll get to that. Anybody else want to ask me anything about enrichment? The process of enrichment is getting rid of the useless to increase the proportion of the useful. You got to have that written down. Increase the proportion of the useful uranium.
What is to increase the
Enrichment is to increase the proportion of the useful uranium. Of the uranium you wanted. All right, ready to launch into the nuclear reaction? You got your enrichment. We got rid of some 238. We can use it for frying pans or for heavy ordnance that's just heavy, not explosive, just heavy.
Is the actual uranium itself radioactive?
I don't think so. It probably is a little, and you should Google that.
Yeah, there's one that we see on that. Whether we should use it.
I mean, I'll bet you it's more radioactive than like gravel and lead and your desk. But to some degree, everything is radioactive. Like a banana has measurable radioactivity. There is nothing which is unradioactive. So on the spectrum, 238 is probably up there. But I don't think it's.
Much above like the background level.
It can't be too far above background. And somebody should Google this because I hate to get my foot in my mouth. Again. Thank you, Sam. All right. Here comes a bunch of content that's separate and critical. We are further behind than when we started, by the way. some of these elements are written in a dark gray. You see them, how it's kind of like bold, the letters are bigger. What does that mean?
Nope.
Not on Earth. So how do we know that they exist?
Science.
Nerds make them for no reason other than to say they made them.
California, yeah.
You get naming rights, so you might notice a pattern. There's one called Berkelium, and the one right after is called Californium. That's because they were made at the University of Berkeley, thus they named them Berkelium and Californium. And then, to show their science nerd credentials, they made like 10 others, and they're all named after famous scientists. Einsteinium, Fermium, Mendelevium, Nobelium, Lawrencium, Rutherfordium, Dubnium, Seaborgium, Bohrium, Hassium, and Meitnerium.
No.
Yes, they're all indium. They are all man-made. Your distraction is slowing me down. What it means that they are man-made is that is just too wobbly to survive on our planet. You can throw more protons together. Basically, that is modern alchemy. But once you've thrown all that crap together, remember I told you that there's these mysterious forces that are not quite gravity, they're not quite magnetism, but they're kind of like that? People know a lot more than I have said. I don't know jack. But there are people who can map, like when you've got 3 over here and 5 over there, there's a net force pulling a 6th one this way, and nerds can do this. It's pretty neat how they figure it all out. You can map out how many you could stick together. But when you get to be really, really big, if you add one more over here, it'll all break. Like, oh, that doesn't work. And if you add one more over there, it'll all break. There's this tipping point where you can only make them so big before they break. And what is the largest element which exists on our planet without spontaneously self-destructing?
Uranium.
Uranium. That's why we use it as a nuclear fuel. Here comes the reaction. You have to know this. Get ready to write a lot. Uranium-235 is stable on Earth. And uranium-238 is stable on Earth. But for some reason, 236 and 237 are not. Write that down. 235 and 238, sure. 236 and 237, who knows but no. Okay?
230 is stable. 230 is not.
235 and 238, yes. 236 and 237, no.
No.
So watch this. Here it comes. To fuse something is to stick it together. Fusion is assembling parts. Fission is to break something. That's splitting an atom. Look. If you take 235, remember like the stuff we're trying to enrich in the first place to make it more common, what we want is a 235. If you take 235 and you throw a neutron at it, it becomes heavier, 236, and that asterisk means it's unstable, wobbly, hot. In other words, radioactive. When you take 235 and you throw a neutron at it, it goes, uh-oh, 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 and it breaks.
Into. What does your banking do?
I got a lot to say real quick, so hold on. Remember those forces that hold together the atom, how they're kind of mysterious and nobody really, that some people, it's kind of complicated? Okay. When you split an atom, there's a lot of leftover force. There's a lot of leftover energy. So splitting an atom gives off a ton of heat. A lot of heat.
Is how much heat?
Really, really, really exceptional amounts. I don't know how to rate that per atom.
Okay.
But if you can make a bunch of atoms split at the same moment, that is a nuclear bomb, James. When you can split a whole bunch of atoms at once, that's the mushroom cloud. with that tremendous shock wave. So much energy that it basically expands the air and displaces it outward. So if you've ever seen footage of nuclear bomb tests, all the hair and the skin flies back, everything, people get knocked over and all the sand, concussion, and you never hear a sound. It's faster than the sound. That's if you split a bunch of atoms at once. But in order to split a bunch at once, you got to have a bunch that can split at once in the same place. That's what weapons-grade uranium is. 90% and up, that'll all split at once. When people show you in the movies the nuclear reactor making a big mushroom cloud, that is a lie. Nuclear reactors, when they melt down, they get really hot, like a few hundred or 1,000 degrees, and they make a big-ass flame. And yeah, you still get coated in radioactivity. As a matter of fact, they may be as or more radioactive depending on the details. But the big concussive event, mushroom cloud, that's bomb only. You need super high concentrations of 235. Nuclear power plants won't do that. They don't make a mushroom cloud because they don't explode. They just get really hot and they melt. First, second, third.
How do you add a neutron? Like,
Voodoo.
possible jump from 235 to 238,
I think so.
Okay.
I don't know, but I must assume so.
Okay, it just does that.
Yeah, it doesn't happen that often. If you threw 3 neutrons at once, I believe it could, yeah. It's just hard to get the timing right. Yeah.
What would happen if a nuclear weapon hit a nuclear reactor?
Nucleus?
I don't know, it's a very good question.
It'd be like one of those.
Probably it would be
you
almost
film
just
it
as bad as the nuclear bomb, plus a little bit. Okay.
So technically, could we make a nuclear bomb with other things besides uranium, but because uranium's the biggest one, that's why we use it?
A, I know that the answer is yes, we can make nuclear
Plutonium
bombs
bombs.
with a bunch of fuels. B, I don't know what... There are like 1,000 details to make all of those atoms split at once. And that all comes down to those attractive forces. So there's a whole set of physics and chemistry called nuclear physics, which is just about the attractive forces between protons and neutrons. You could get postdocs and still just get one little wedge of that science. It's a whole field of study. So the Manhattan Project was like a couple of weeks about designing the payload, a couple of weeks about like designing the bomb, and then like a gazillion years of a million nerds trying to figure out which mix of atoms and energy, and then whiteboard math, equation, plus and minus. Yeah.
But like you were saying that when you split an atom, like it creates an exceptional amount of heat.
Yes.
That's true for any atom that you split it.
I reckon so, but my hunch would be that splitting a bigger atom would release more energy because there's just got to be more attractive forces in that nucleus, right? I would think.
Makes sense.
Yeah, it makes sense, yeah. Now, everybody, I'd like to get away from this conversation to discuss one concept, and we'll come back to this conversation. Imagine, I have built a Lego castle on Violet's desk. And because she's a girl and women love to cause pain for no reason, she'll push my Lego castle onto the ground and it'll break. And I'll go, oh! And she'll go, wah, ha, 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 as women do. Everybody got that? Now imagine I built an identical castle on all of your desks. And everybody pushes them off at once. And they all break when they hit the ground. We could probably find a little structural weakness in my Lego castle, like maybe that little piece over the doorway that when they hit the ground, you know it's going to break there. And the place on the back where there's just like 2 buttons holding it together, you know it's going to break there. So on average, we get a left side, a right side, and some little pieces. Do we agree that there would be an average of breaking 100 Lego castles at the same time? Yes? And there might be some pieces that always come loose. Like those stupid little flagpoles that never stick on. You know how the flagpoles always break off? So we know that there's going to be like 3 to 5 flagpoles plus a left half and a right half on average. Yes? Agreed?
Yes.
See?
Now watch me. Inside of a nuclear reactor, we have about 3% uranium-235. When you throw a neutron at it, and Gabby, I really don't know, you use neutron-emitting atoms. So you basically have to have something which is radioactive enough to bail out neutrons. And to have a known rate of neutron decay, so you just bring them close to each other until the neutrons, you can guess, have left at a certain rate. Then you remove that sparker, so to speak, and you've thrown in neutrons enough to start the reaction. Watch. You've made 236, which is inherently unstable. It splits. There's no sound. There's no mushroom cloud. You just get heat. But everybody look up. Look up. You'll get radioactive decay products. On average, from a conventional old school reactor, these are the reactors that were built in the 1970s, okay? The average for most reactors is molybdenum 103, tin 131, and about 2 free neutrons. That's the average. It could be a bunch of other stuff, but the average is molybdenum 103 and tin 131. You have to know that. The average decay products are molybdenum 103, tin 131. And it's a good thing you already wrote all this down in your notes. Yeah.
If adding a neutron to uranium creates 2 free neutrons, will like chain reaction with other?
Nerd award! Nerd award for Monroe! Hold that thought, we'll be back. Now, remember I told you that the little atoms can't hold any neutrons, and some of them can't hold any extra, and some of them can only hold a few extra, but the really big stuff can hold a lot of extra? Remember I said that earlier? What's really scary, please look up, about molybdenum 103 and tin 131 is that those are really overloaded with neutrons. This is something you've got to know, and you have to be able to explain it. Splitting an atom into 2 smaller ones gives you stuff that's more radioactive than you started with.
Why?
Because uranium can hold about 30 extra neutrons, no problem. But when you split that, molybdenum cannot carry 9 extra. And tin cannot carry 13 extra. You know, there's a tow truck that can pull a tow truck, but my car cannot handle carrying the weight of another Tacoma, let alone another Tacoma plus other crap. So, here comes the bottom line. I'll try to answer, but everybody please try to follow with me. The 235 had way more neutrons than protons. It had 92 protons and about 150 neutrons. That's a lot of extra neutrons, but uranium can pretty much hold that. When you split that into, on average, molybdenum and tin, those smaller atoms, all those extra neutrons between them, they really cannot hold them. In other words, these are really heavy. They will continue to decay. They will continue to be radioactive. The products are more radioactive than the fuel was. Don't check out. Try to keep this in your notes. These are key issues. Yeah.
But how radioactive is uranium-235 anyway?
A little bit.
How do you measure how radioactive?
It's called physics. I mean, the units of radioactivity measurement are Sievers, and it's basically a measure of their energy. And it's a type of energy that is the attractive force between neutrons and protons, and so I don't know how to explain it better, because I don't get it. Now, what did it take to start this reaction? A neutron? And Bobro, what's the problem with these decay products? And what else are we going to find in the reactor? A bunch of other 235, right? So I have an idea for you. I'm going to fill this classroom with firecrackers. And I'd like to warm my hands by setting off one of them. Why is that a bad idea? Because the what? It's a chain reaction. When the first one goes off, those sparks will light 100 others, and those hundreds will go off and light 100 other, or a million others, right? Agree with me? Chain reaction. Inside the reactor core, you've got about 3% uranium-235. When you split one of those, you get neutrons. And the rest of the stuff is going to keep spilling neutrons as well. Understand what I'm saying? And so, if you just threw a neutron at a reactor core and walked away, you guys know what exponential growth is, right? The heat would go up, which encourages the reaction, which gives off more neutrons, which gives off a lot of heat, which encourages the reaction and gives off a lot more neutrons. That's the exponential growth of heat. That's what we call a meltdown. Because it literally melts, and we call it down because it'll literally sink itself into the Earth's crust because it gets really freaking hot. Yes?
It doesn't actually go to China, though.
No, it doesn't go all the way to China.
It doesn't go. It doesn't really go that far, though, right? Doesn't,
I mean, we would come out somewhere in the Indian Ocean, but it doesn't go that far, no.
no.
It just goes a little bit.
Yeah, I don't know.
Yeah. Yes?
Is that caused by human error, or is it just spontaneous?
Well, remember what I said. I want to warm my hands on one firecracker at a time by lighting one in a room of constantly thickly packed. Right? There's two things I got to do. Keep those sparks from traveling, that's called moderation, and take away the heat so I don't encourage more reactions. That's called the coolant. It's a full-time active process to prevent the rest of the snowball effect. So when humans stop working at any of our planet's nuclear power plants, you start the countdown. And within a few minutes or a few hours or a few days, it's a meltdown. There's no plan B for that. Like there's sparks in the firecracker storage right now.
So like if Homer Simpson passes out eating his donut and forgets to click the coolant, then it'd be a meltdown.
AKA 3 Mile Island, Chernobyl, Fukushima. We're going to break them tomorrow, but I want everybody to see two things before you leave today. I've got just a couple of things to show you. Even if the bell rings, I need you to stay for these two things. Does everybody understand why we're scared of too much heat? It encourages these reactions. And does everybody understand why we're scared of the neutrons? Because they start more reactions. So now please look up. In the reactor core, there are two key functions you may not leave. One of them is called moderation. To capture those neutrons, we need control rods, substances that absorb neutrons. The other key function in the reactor is called cooling. We have to keep cold water flowing at all times. At 3 Mile Island and Fukushima Daiichi, it was the coolant that failed. At Chernobyl, it was the moderators that failed. I'll see you guys tomorrow. Bye-bye.